All right, now we are going to, you have learned about how ionization energies are measured with photoelectron spectroscopy. We are going to look at some ionization energy data. So our learning targets, our first one, again, was recognizing that the arrangement of electrons is important because it relates to the properties of elements. What we're going to do in this talk mainly is analyze actual data in order to try to develop an understanding of how these electrons are arranged. And we're going to relate the organization of electrons and atoms to the organization of the periodic table. All right, so these are the data from photoelectron spectroscopy. We've got elements lined up, hydrogen, helium, lithium. We've got multiple numbers after each element because all these elements except hydrogen have more than one electron, so they have more than one ionization energy. All right, so this row that I've highlighted in yellow is all the element symbols. Above that are the atomic numbers of all the elements. All right, so let's review your first prediction. If you reasoned that as we go from left to right here, the atomic numbers are increasing, the atomic number increasing means higher charge in the nucleus. That should mean, all other things being equal, a stronger attraction to the electron. Then you would expect the ionization energy to go up as we go left to right. Okay, so we look at fluorine has a larger ionization energy than oxygen. And neon has a larger ionization energy than fluorine. But something happened here. It didn't go up going from neon to sodium. It dropped way down. All right, let's take a broader view of the data. So in science, we often make sense of numerical data by plotting it different ways. Let's make a graph of these energies to remove the first electron from all the different elements and see how it relates to our predictions. So here I'm selecting the element names and the first ionization energy, the energy to remove the first electron for each one. And here's the graph. Now we have some sections where ionization energy is more or less increasing, and then we have these big drops. Whenever we see something like this, it's important. Figuring out the reason is going to help us understand how the electrons are arranged. Let's look at where the drops occur. We have helium going to lithium, neon going to sodium, and argon going to potassium. Let's find these elements on the periodic table. So here we have helium, neon, and argon. The elements at the peaks are all on the far right, and lithium, sodium, and potassium, the elements in the valleys, on the far left. So we're already seeing a connection with the periodic table. Each of these elements has one more electron than the element before it, but that last electron doesn't require much energy to remove. If it doesn't take much energy to remove it, the attraction of the nucleus must be weak. What kind of arrangement would lead to a weak attraction? Maybe the distance to the nucleus is more. When we go from the end of a row on the periodic table to the beginning of the next row, the electrons get a lot farther away from the nucleus. Or maybe just the last electron added is far away. Anyway, if the electrons were farther from the nucleus in lithium, sodium, and potassium, then the attraction would be weaker and it would take less energy to remove them, which is what we see. Because we saw the same thing each time, right? We went all the way across a row with the ionization energies more or less increasing as we predicted, and then there was a big drop at the beginning of the next row. All right, let's look at your second prediction. Recall how the electron cloud shrunk as we removed electrons. Did you predict the remaining electrons would get closer to the nucleus and need more energy to remove? Let's look at the data. So here I've selected oxygen, We're going to plot the successive ionization energies for oxygen. That is the energy needed to remove all of the electrons one at a time. Note this is a different scale because we're now looking at removing all the electrons from one atom rather than comparing the energy to remove just the first electron from a lot of different atoms. So these are much higher energies. If you predicted it would take more energy for each successive electron, you were right. But there's something interesting. 2 electrons at the end take way, way more energy than the ones that came before. Oxygen seems to have 2 electrons that are much more strongly attracted to the nucleus than the rest. Let's see if anything like that happens with other elements. Okay, let's look at boron. Again, the prediction that energy to remove electrons would go up as we remove more is correct. And again, there's a big jump. And again, there are 2 electrons after the jump. That means 2 special electrons that are really tightly held by the nucleus. Let's look at an element with a lot of electrons, potassium. Again, we have the last 2 electrons needing a lot of energy to remove. But look, there seems to be another break in the data going from electron 9 to electron 10. This plot shows the logarithm of the ionization energy. A log scale can be helpful in seeing patterns in data that are spread over a very large range. You can see 3 breaks in the data. We have those 2 electrons at the top. Then there's a group of 8 that are pretty high energy, pretty tightly held. Then another group of 8 that are lower in energy than those, not so tightly held. And then another big drop and 1 lone electron with a very low ionization energy. Recall, it's very easy to remove 1 electron from potassium. Looks like it's not so easy to get the rest of them. Do we see these groups of 8 with other elements? Calcium. Here's calcium, 1 more electron than potassium. We see there are now 2 relatively low energy, but looking at the top, we again have 2 that are held far more tightly than the rest. And then a group of 8 that are tightly held, then 8 less tightly held, and then those last 2. This is sulfur. Once again, 2 electrons are most tightly held, then a group of 8, then at the low end there are 6. Not enough electrons in sulfur to make another group of 8. Here's aluminum. Again, we have 2 at the highest energy, then a group of 8, then in this case the leftover group is only 3. In fluorine, we have the 2 at the top, and the rest are all pretty much grouped together. There are 7 in this group, so if a group holds up to 8, they will all fit in the same one. All right, making sense of this, in every element we had 2 electrons that took a lot more energy to remove than all of the rest. Remember, we're talking about energy needed to remove electrons. So 2 electrons are held extra tightly. Possible explanation? These 2 electrons are closest to the nucleus. Remember, charges interact most strongly when they're close together. So the model so far, we have 2 electrons really close to the nucleus. All the other electrons are farther away. This would explain why 2 electrons require the highest amount of energy to remove. So consider the groups of 8 electrons. For elements that had enough electrons, there was a group of 8 at pretty high energy, and then anything beyond that was lower. This suggests another shell or another sphere outside the first 2, but inside all the rest. So the model so far, here we have 2 electrons close to the nucleus. Those are the ones that take the most energy to remove. And then we have a group of up to 8 electrons, and all of the rest of the electrons are farther away. So adding detail to the model, recall we saw that potassium and calcium each had 2 groups of 8 electrons, implying that there's another shell that can hold up to 8. So now what we have is potentially a series of shells. Shells are concentric surfaces having a constant radius. The first can hold 2 electrons. The others can hold 8 electrons. So this represents calcium, 20 electrons total. This model is called a Bohr atom after Niels Bohr. It accounts for all the observed trends in electron energies. Note that each shell corresponds to a period, that is a row on the periodic table. The electrons in the outermost shell have a special name, valence electrons. Normally, only the valence electrons interact with other atoms. Thus, it is the valence electrons that are responsible for most of the properties of an element. So our next steps are going to be to practice drawing Bohr atoms and identifying valence electrons.